Alright, so for this video we're just going to focus on one problem. It's a second law problem in 2 dimensions. And this is, this is pretty complex, and it's likely that we're not going to run into this situation. And also, a situation like this is almost, you can almost simplify it more by just changing the orientation of the coordinate plane. For this though, we're not going to, just so we can see what it entails if we don't. So we have this particle it's got a force pulling it this way, like 30 degrees south, I guess, of negative x. Got this force pulling it this way with 15 newtons. And then it's experiencing an acceleration of 4 meters per second squared, and the direction of it's 40 degrees above positive x. And so we're asking, so it's getting pulled this way and this way, but it has acceleration like this way. And so what that means is there's some other force acting on it to cause it to accelerate that like that. And so we need to figure out what that force is. So we'll call that force F3. Alright, and so to do this we need to do net force equations. Okay, and so we'll start with the net force, say, for x. Okay, well, in this direction we know, let's just add the forces here. So we know that there's some component of F3. Okay, we know that F1 is acting entirely up and down, so that will have 0 force acting this way. Then we also have the x component of F2, so this would be 20 newtons times cosine of 30. Okay, now this is going to all be equal to the mass of the object, which I didn't give. We'll say the mass is equal to 2 kilograms. Let's say the mass is equal to 5 kilograms. Okay. And so what we need to figure out for this part, the acceleration, so the mass of 5, and then for the acceleration here, it's going to be 4 times the cosine of 40, since it's only the part of the acceleration acting in this horizontal direction. Okay, and then we can actually solve this for F3, the x component, because it's going to be equal to 20 newtons times cosine of 30 plus 5 kilograms times 4 meters per second squared times cosine of 40. Okay, so we can simplify all this to find that the x component of F3. We simplify and we get about 32.6 newtons as that x component. Now we want to find the y component. Okay, and so to find the y component, we're going to do net force equation for y. Okay, so the sum of the forces in the y direction. So what are we going to put on this right side? 5 kilograms times what? In this case it'll be 4 times sine of 40. Okay, that's a 40 right there. And then overacting this way, we have the upward F1, 15 newtons. We have downward F2, the y component, so that'd be 20 times sine of 30. And then we have here Fy. So Fy would be equal to 20 times sine of 30, which sine 30 1/2, so we'll just write this as 10 newtons, minus 15 newtons for that upward force, and then plus 20, it's 5 times 4 is 20, so times sine of 40. Okay, so we can work this out. So we get here that this simplifies to be like 12.9 newtons. So then Fy is equal to 10 newtons minus 15 newtons plus 12.9 newtons. So that would be like something like 7.9 newtons. Okay, for Fy. Alright, and so then the last thing for us to do here is to go ahead and find the magnitude and direction of F3. So magnitude will be the Pythagorean theorem, we'll say the square root of 7.9 squared plus 32.6 squared. And then the direction, so it's going to be something like 32 this way and 7.9 that way will be this angle, which we'll find using inverse tangent of the opposite over the adjacent, which in this case would be, so that'd be 7.9 over 32.6. And so we get that F3 has a strength of 33.5 newtons, and it acts at a direction of 13.6 degrees above positive x. Okay? And there you go. That's a two-dimensional problem. It was a lot of work. And we're not going to see a ton of this because, like as I was saying with those, like we did with those inclined plane ones where we rotate the coordinate plane, it's easier just to treat acceleration to put it in one dimension. So if we took the magnitude and rotated the coordinate plane, that would probably be an easier approach.